Hello, everyone. I'm Ron, and alongside Sunit, we will be presenting our project where we will use transformers for pill classification. You can move on to the next screen. So our objective is to introduce another classification method for the ePill benchmark and to observe how it performs. Having a better method with a better classification accuracy could benefit people who have to take and separate many pills. So this could help them mitigate confusion or misadministration, which could be potentially hazardous. So before we begin talking about the method, we want to introduce this data set quickly. So for the project, we're working with an ePill data set, which is a benchmark composed by researchers from Microsoft. And what they did is they combined the NIH challenge data set and the NIH pillbox data set. This resulted in a data set with over 13,000 images of pills. We can divide these image types into two different subsets. So on one end, we have the consumer images, which are images that have been shot with controlled lighting and with professional equipment. This set covers 4,902 different pill types. And this means that we have 9,804 different classes because we consider each side of a pill its own class. We also have the reference images, the set of reference images. These are images that are taken in a real-world setting with uncontrolled factors such as lighting, background, and equipment type. The pills that we see here, they're not new types of medications. These are some of the same classes that we see in this consumer images. So these total classes in the reference images, they're part of the same set of 9,804 different classes. So we have a total of over 3,000, almost 4,000 reference images. And the big takeaway from all this is that only 19% of the data set is repeated. The vast majority is only observed once, either during training or testing. What this means is that we're not facing the conventional classification problem, but rather a few-shot classification problem. So to address this, the researchers came up with this data set, with this architecture. Where they take in pill images and pass them through a CNN backbone that maps and the results, the features that result from the CNN go through an extra layer of embedding and actually diverge into two different classification heads, which allow some of these classes that we see here, these losses that we see here to be calculated. The heads aren't pictured in this diagram here, but we have one margin head, which projects an output that allows the cosine softmax loss to be computed. And then there's also a binary head, which computes our contrastive and triplet losses. So what we want to propose is that we take the CNN and replace it with a transformer. You can hit the next button. Yeah, and so transformers have shown to outperform CNNs in many classification tasks. And as such, we see their use for a few-shot classification, not only potentially a suitable alternative, but one that could maybe improve the overall accuracy of this model. And so now let's discuss some of the losses that we just saw. The first one is the cosine softmax loss, otherwise known as the arc phase. The goal of this loss is to maximize the margin between different classes and to minimize the intra-class separation. So we want classes that are different as far away as possible and classes that are close as possible. So the first term that we see is the theta term, which is the theta y, which is the angle between our feature xi and our ground truth center, which is a weighted matrix wyi. Then we have another angle, theta j, which is the angle between our feature xi and the weighted matrix wj, which is learned throughout epochs. We have s, which is our scaling factor. And the way that it's computed is we take the exponential of the cosine of this angle times s, and we divide that by itself plus the sum of all the exponentials of the cosine of theta j times s. And then we take the negative log of all of that. And now we can move on to the next loss, which is contrastive loss. So the contrastive loss is essentially another similarity metric. This loss should be small when two pairs of samples are the same and large when they are different. D is distance between two images. M is a predetermined distance that we set, a threshold, and Y is a binary variable, which tells us if the two images are the same or not. So which side of the equation is actually used in this loss is contingent on whether the images are similar or not. If the images are similar, then the left side becomes 0, and we just take the square of the max of 0 and the difference of the threshold and the distance. And if y is 0 and the images are not similar, then we omit the right side and we just square the d. So let's move on to the triplet loss, which is our final loss. So this loss takes in an anchor sample, a positive sample, and a negative sample. So the anchor sample is our reference sample, if you will. A positive sample is a sample that is the same kind of pill as an anchor sample, and the negative sample is one that is not like the anchor sample. The f right there that we see is an embedding function, and the alpha variable is a margin between these pairs. So the goal of the triplet loss is to create an embedding space in which the anchor and positive samples are close together while maximizing the distance between the anchor and the negative samples in that same space. This is done by taking the L2 norm of the embedding of the anchor sample and the positive sample of the difference of those two, and then also taking the L2 norm of the embedding of the anchor and also the embedding of the negative sample, the difference of those two, and then subtracting the two and adding in a margin. And so we can move on to the total loss or the final loss now in the next slide, which is just the aggregation of the standard cross entropy loss and all of these losses that we've just covered. The lambda parameters that we see are just weights that scale our losses, and these are empirically chosen. And one thing that we want to note is that in one sense or another, all of these losses that we've just covered are essentially just attempting to maximize the distances between similar and dissimilar pills. They just do so through different methods. And now we'll pass it off to Sunny for the rest of the presentation.
All right, thank you, Ron. So I want to now dive into the results we got. But before doing that, I want to talk about the metrics that we'll see being measured for our results. So the first metric we have is GAP, and this is short for global average precision. And basically what this does is it validates the ranking consistency and the confidence consistency of our queries in our data set. So here, N is the number of predictions we're doing, and M is the total amount of queries. P of I is the precision of the ith prediction, and rel of I is the classification result of the ith prediction. So usually that's a percentage of confidence. So both of those are multiplied together and then summed all the way up to the number of predictions we have, and then normalized by the number of queries we're using. The second metric we have is MAP, and that is short for mean average precision. And what this does is it basically measures the accuracy / correctness of each query. And so what we're doing here is we're going through each of the classes 1 through N, and we're taking the average precision, AP, that's what it stands for, of the ith class, and then we're normalizing it by the number of classes that we have. So now that we know what metrics we're using, I'll go ahead and jump into the empirical results that we got. So in our case, we opted for the multi-headed learning, and we are using the both sides data set for prediction. Now you might see here some unrecognized stuff. So we have a gap at 1 here and a map at 1 here, and you might be wondering what that is. Basically, that tells us the top pill, the gap and map score at the top pill type for the queries used in gap and map. So we're just considering that top one in both of these metrics, but they're still using the same algorithm. So for our baseline, we use the ResNet 50, and we use that because that's the default one used in the paper and in the code. And you can see that compared to the other results, it did pretty good. Not quite as well as the paper, which I'll discuss a little later, but still better than our results. So our best performing model was a SWIN version 2 transformer based model that was pre-chained with an extra embedding module. As you can see, it got the closest to our baseline here. However, it's still not as close as we would want it to be. There's still a lot of improvement I think we can do to catch it up to this. When just using a pre-trained Swin version 2 transformer module, this results are slightly worse, I think, than the pre-trained plus extra embedding. However, when using the extra embedding without any pre-training, the results are pretty terrible. As you can see here, there's a huge margin between these two of our models in this last one. And we think maybe this is more has to do with the training time, because we use the same training time for each of these. So it needed more time to actually learn the weights, whereas these two had the weights already learned, so they didn't have to do as much training.
Okay, sorry, I want to interrupt you here. So give you some feedback. So here, yeah, this rank 1, just to give other student. So when this is actually like a retrieval problem, right? So you have a query, right? You want to know what pill type, right? You match that with the reference, and if you retrieve like maybe 10, if the ground truth is within that 10, then you can say that's a correct match, right? But here is more restrict, right? You only you select the top 1. If it's wrong, then it's wrong. Okay. So if you allow like arrows, right? If your ground truth is within the top 5 ranked similarity, right, retrieved, that will also consider to be correct. But since here we are doing like pill classification, we want to using the top 1 rank. And here, I'm not sure how you train. So when you have the Swing V2, supposedly, right, these vision transformer model should be, if you pre-trained on ImageNet 1K, you should have better representation than the ResNet, supposedly. And so when you're using this transformer, are you freeze the entire weights, or do you do fine tuning, or are you adding maybe adding a pen like 1 or 2 small layers, just fine tune that layers?
I believe or go ahead, Ron.
We found that the best results were not with any freezing of any layers. So the only thing that we're changing in those Swin transformers is the outputs of the linear outputs, because we have a different amount of classes.
Yeah, can you go back to the pipeline you have? Let me see the pipeline. Yeah, here, this backbone is basically you can using that as a feature extractor, right? Basically.
Yes.
So I would thought, okay, if you're using the Swing transformer, if you keep the weights, the pre-trained transformer weights frozen, right? Maybe you only tune maybe a couple of the embedding layer, or maybe a couple of linear layer, that would be the best way to go. So, and I think that should work better than the ResNet 50. So did you try like froze the transformer and only maybe adding one or two small linear layer?
So yeah, we did try that, and yeah, like I said, the results weren't that great. Maybe it needed to be trained for more epochs, but so we didn't add any extra layers after freezing that, because the embedding layer already has some other projection layers inside of that.
Yeah, just fine tune that embedding layer, right? So maybe you can add one more if that's not enough. Just fine tune those layers, and also you need to maybe adjust the learning rate, because you are doing a very small amount of fine tuning, right? So and also the loss term, I don't know if you want to adjust. You have a couple of weights there. That maybe also need to be adjusted.
Okay, yeah, we can try choosing different weights. We just went with what they empirically denoted were the best weights, the best lambda parameters for those losses.
This should change.
Okay.
Yeah, you can try those things, and hopefully you guys can bump up, maybe further boost the performance. Okay. Okay, yeah, with this slide time limitation, yeah, we can end here. So do you have any other questions for the project you guys have so far? The problem you guys encounter, anything
I guess I don't. Do you, Sunny?
Are you asking for any of the problems?
Do you have any
Wait,
other problems you want to discuss here?
Oh, yeah. One of the problems I was going to talk about in the conclusion is that the code that was provided was kind of, I think it wasn't very good quality because we ran into a lot of issues with training. More specifically, when we trained our model, it didn't get the same results that were advertised in the paper.
Yeah,
And that was without changing anything. We just ran the
Yeah.
default model. So that was concerning. Also, for some reason in the epochs, it wouldn't go, it seemed like it wasn't going through all the iterations, the epochs, the training code. So that was also really concerning, and we don't know why. We actually emailed the authors of the code about that. And as of today, we don't have a response of why that
Oh,
happened.
yeah, I don't think you should rely on other people to respond to your question. So you guys can go ahead and maybe dive into the code, right? Because
Mm.
some of them may be easier, for you guys to solve directly. Maybe you can switch out some of the portion, or maybe write yourself, right? If you think that give you some of the issue. Yeah, but I think now you're just switching the backbone. Yeah, there's a lot of flexibilities. You guys can, write the code, implement the code yourself, so that you may not encounter the similar or the same issue.
Okay.
Okay, great. Yeah, if you guys have any more details, questions, I'll be happy to answer that during the office hours. But thank you for the update. And then, yeah, this is you guys making good progress. But just take some of the suggestions I have and maybe further improve the results. Okay.
Great. Thank you, Dr.
Okay.